All right, continuing with lesson 2, which is using the number line to model the addition of integers. We're going to focus now on vectors. So let's look at a couple examples. The directions say to create a number line model to represent each of the expressions below. Now we are kind of using that bump method. So we start at 0. And my first number here is -6. So I am going to go 6 units, because that's the absolute value of -6, to the left because the negative tells me the direction. So I'm going to go 1, 2, 3, 4, 5, 6. Now I'm at -6, and I'm going to add 4 to it. The absolute value of 4 is 4, so I'm going 4 units. It's a positive 4, so I'm going 4 units to the right. 1, 2, 3, 4. And I see that I end up here at a -2. Now, this is not a vector. A vector is a straight line. So what I want you to, one of the ideas you could do is you could start with this bump method and then go over it with a vector, because I don't really want just the bump method. So if I start at 0 and I take a straight line and go over it, maybe even use like a highlighter on something, we want to get used to using these vectors because we use those more than the bump method. So I go left 6, and then from here I go to the right 4. And you can see that I put my solution of a -2. Okay? I want to make sure we're answering the question being asked. And what is the answer? It is a -2. Okay? So you can use that bump method with the vector over it, or we can just use vectors. Our first number here is a 3. The absolute value is 3, so I'm going to move 3 units, since it's positive, to the right. So from 0, I'm going to go 3 units, 1, 2, 3, to the right. Now from there, I'm going to go 8 units because the absolute value of -8 is 8. So I'm going to go 8 units. The negative sign means go left. So from the 3, I'm going to go 1, 2, 3, 4, 5, 6, 7, 8. It's a little bit harder with the vector method. So that's why I'm okay if you want to use like that bump method with the vector over it. But always don't forget to answer the question being asked. What is 3 plus -8? It is a -5. Okay, so I am good if you do this, or I'm good with just the vectors, but I do need to see those straight lines. Okay, this is representing addition on a number line. This whole lesson's about. So find the sums of integers represented in the diagram below. Now remember, we started at 0 right here. Looks like we are going to the right 5. Then from 5, we're going to the left 2. At 3 then we're going to the right 3. So when it says write an equation to express the sum, we need to write down what I just was talking about here. From 0 to the right is 5, plus, so I'm doing a sum here, I am going to the left 2 units. Now I'm going to put that in parentheses, and the reason is only for neatness, because sometimes I will see that, and people are like, well, it's negative. And I'm like, how can you tell? It just looks like you kind of forgot to pick your pencil up off the plus sign. Oh, no, it's a negative. But if you put parentheses around it, then I'm more likely to believe that it's negative. So those parentheses really are only for neatness, because sometimes, myself included, we get a little sloppy. All right, so we've gone 5 plus our -2, now plus 3. And we're almost done, except this is an equation, so I need an equal sign. So I put my equal sign in. And I know this isn't necessarily following the rules of I have to have a variable, but I told you that was just kind of my thing when we're writing equations. So this equation here represents 5 plus -2 plus 3 equals 6. So what 3 cards are represented in this model? Think back to the last lesson we were talking about integer cards, and you're just thinking about you have cards in your hand, like your homework you were doing. Well, you can add opposites to make the numbers stay the same. So don't overthink this. The 3 cards that are represented here are just the 5, comma, -2, comma, and a 3. Excuse me. And how do you know? Well, that's the length of the vectors. So I'm just going to say the vectors. Remember, vectors are just those arrows. Okay, vectors tell us the absolute value. They tell us how far we're going, and they also give us the direction that we're going in, either right or left. So in what ways does this model differ from the ones we used in lesson 1? Well, the big thing is in lesson 1 we use those hops or the bump method. So I'm just going to say we're using vectors instead of hops, bumps. I can spell it right. All right. It says, can you make a connection between the sum of 6 and where the third arrow ends, the third vector ends? Well, our sum is when the solution to addition problem, and our third vector ends right at that sum. So I'm going to say the final, in this case it's a third, the final vector shows us the sum of 6. The final vector where it ends up, that's the solution. And it said, would the sum change if we change the order in which we add the numbers? For example, -2 plus 3 plus 5. Well, we can try it. So we could start at 0 and go -2 and then plus 3. 1. Oh, and then I messed it up again. Sorry, guys. I'm going to start over. Start at 0, and I'm going to go -2. And then from there, I want to go 3. So there's 2, 3. And then from there, I want to go 5. 1, 2, 3, 4, 5. Okay, so you can see that we're still going to end up in the same spot. And we knew that because the commutative property says we can change the order. So will it change? No, because of, oh, sorry, this is sloppy, the commutative property. And would the diagram change? Yes. Yes, it would. Okay. The vectors are in a different order. But let's write that down, then I'll show you something. Okay. So we know the sum is not going to change, but is the diagram going to change? Yes. They're in a different order, period. But if you look, I still have the same vectors. I have a -2 and a -2, a 3 and a 3, a 5 and a 5. So I still have the same vectors. So I'm still having that same absolute value. I actually still have in the same direction. So the vector lengths aren't changing. They're just occurring in a different order. Okay, so the big difference with this lesson is that we're starting to use vectors instead of the bump method. But remember, if you are more comfortable with that bump method or hops or however you want to say it, feel free to draw vectors over it. The important thing is to make sure you're going the right absolute value, the right distance, and the right direction.